So welcome Michael Wibmer from Aachen, and here to speak on Jordan-Hölder Theorem for different algebraic groups.
Okay, so thanks a lot for giving me the possibility to speak here. So I'll be speaking about different algebraic groups, and roughly these are groups defined by algebraic difference equations. And one motivation for studying them is that they occur as the Galois groups of linear difference or differential equations depending on a parameter. And so I will not properly explain this Galois theory, but I would like to motivate what is going on in an example. And this is really very similar to the parameterized Lisieux theory, which was explained by Carlos before. So you have this is a Bessel's equation. That's a linear differential equation, and it depends on this parameter alpha here. And the Bessel function J alpha is a solution of this differential equation, but it's also a solution of this difference equation. And so the usual theory for linear differential equations, there the Galois groups are algebraic groups, and they measure the algebraic relations among the solutions. So the usual Galois group is not able to see this relation among the solutions, because that's not an algebraic relation. That's really a difference algebraic relation. And you need a difference algebraic group to see this difference algebraic relation. And so Charlotte Tallois and Lucia Di Vizio and myself, we developed a Galois theory which is able to handle this type of relations. And there the Galois groups are difference algebraic groups. And in this case, you can compute this difference Galois group, and it's given in that form. And so sigma here is just an endomorphism. And I will properly explain what this really means on the next slides. And so one of the motivations for studying the structure theory of difference algebraic groups is that eventually that should help you to construct algorithms for computing these difference Galois groups. Okay, but so to properly explain what is a difference algebraic groups, I will first recall the basic definitions from difference algebra. And so a difference ring is a ring, so all rings are commutative here. The difference ring is a ring together with a ring endomorphism, which is usually called sigma, and we do not assume that sigma is injective or surjective. And so difference rings, they're really the basic objects in difference algebra, like commutative rings are the basic objects in commutative algebra and algebraic geometry. And so a difference field is just a field with an endomorphism, and the classical example is that you take the rational functions with the shift operator, so sigma of f of x is f of x plus 1. So from now on, we will work over this fixed difference field, and so we consider difference polynomials over this difference field. So the difference polynomial ring in the difference variables by 1 up to yn, that's a polynomial ring in infinitely many variables. And so you have y1 to yn, sigma y1, and so on. And here you have an action of sigma, which is determined. So the action here is as it is suggested by the names of the variables. And then if you have any set of difference polynomials, possibly infinite, so you also can call this a system of algebraic difference equations, and then you can look for the solutions of such a system in any K-sigma algebra. So a K-sigma algebra is just a K algebra together with an action of sigma, such that the sigma on R extends the action of sigma on K. And so the solution are just all points in a fine space over R, which such that all elements vanish on these points. And so essentially, a difference variety is the set of solutions of such a system of algebraic difference equations. But from a formal point of view, you can say that it's a functor from the category of K-sigma algebras to the category of sets, which is of this form. And a morphism of difference varieties is then just a morphism of functors. But essentially, that just means, okay, it's a map given by difference polynomials. Okay, so now we can already define difference algebraic groups, and essentially a difference algebraic group is a difference variety with a group structure or from a more formal point of view, you can say it's a group object in the category of difference varieties. So examples, you can think of algebraic groups as being difference algebraic groups, just because you can think of algebraic equations being difference algebraic equations. So you can think of difference algebraic groups as being a generalization of algebraic groups, and in fact, so difference algebraic groups have a lot of properties in common with algebraic groups. So this is the example from the beginning. This is the sigma-Galois group of Bessel's equation. So here sigma is applied to the coefficients of the matrix. That would be an example of a difference algebraic subgroup of the multiplicative group. But here you can also take other exponents if you like. And any linear difference equation defines a difference algebraic subgroup of the additive group. So here the lambdas are elements in the base field, so that's the well-known superposition principle for solutions of linear difference equations. So if you add two solutions, it is again a solution. And so the last example is something like the generic version of the unitary group, all invertible matrices, such that G times sigma of G transposed is the identity matrix. And so you see, if you take here R to be the complex numbers and sigma the complex conjugation, you really get the classical complex unitary. So some easy fact, so the category of difference varieties is anti-equivalent to the category of finitely sigma-generated K-sigma algebra. So this finitely sigma-generated, it just means that you can write the algebra as a quotient of the difference polynomial. And then you immediately see that the category of difference algebraic groups is anti-equivalent to the category of finitely sigma-generated K-sigma Hopf algebra. So K-sigma Hopf algebra is just it's a Hopf algebra over K such that the structure max, so the Hopf algebra structure max, commute with sigma. So this is really very similar to the theory of algebraic groups. So you know, algebraic groups are anti-equivalent to the category of Hopf algebras which are finitely generated as algebra. Okay, and so if you have a difference algebraic group G, you denote the corresponding Hopf algebra with this KG. And in this setting, so a sigma algebraic subgroup of G corresponds to a sigma Hopf idea in this. So we also call this KG the coordinate ring of G. So it corresponds to the sigma Hopf idea in the coordinate ring. So that's just a Hopf idea which is a sigma idea. Sigma idea means that it's stable under sigma. Okay, so we can now we've seen some basic basic definitions of different algebraic groups. We can start discussing this Jordan-Hölder theorem. And so that's the classical version for finite groups. So if G is a finite group, then the statement is that there exists a so-called decomposition series. It is a subnormal series, meaning that each group is normal in the preceding one, and the quotients are simple. And if you have another such decomposition series, then these two series are equivalent in the sense that they have the same length, and the quotient groups are isomorphic up to a permutation. And so in the classical case, the existence is really easy. So what you do is you just look at the in the set of all proper normal subgroups, you take a maximal one, call it G, and that's your G1, and you go on like that. Because the group is finite, the construction terminates, and that's it. So really the harder part is the uniqueness here. And this, so there's different ways of doing it, but so I think that it's kind of the standard proof now goes through the so-called Schreier refinement theorem, which says that any two subnormal series of G have equivalent refinement. And so I should say that the Jordan-Hölder theorem for algebraic groups was proved by Rosenlich, and Jordan-Hölder theorem for differential algebraic groups was proved by Cassidy and Singer in 2011. But before we can even look at the formulation of the Jordan-Hölder theorem for different algebraic groups, we need to discuss some more notation and results on different algebraic groups, because you see even in the statement you have these quotients occurring, so we need to discuss the quotients, and we need to have good properties of the quotient, and it's not so obvious actually how to even say what is a quotient, because so you cannot just form the quotient by taking cosets. That would be just too naive, that it does not really work. But what you can do is you can define it through a universal property, but then the problem is that you have to show that this universal property can be satisfied. Okay, so you have to construct this universal object, but okay, it's possible. And so the statement is that if you have a different algebraic subgroup, so if you have a normal different algebraic subgroup of a given different algebraic group G, then there exists this morphism of different algebraic groups, such that for any other morphism which is a property that n lies in the kernel of the morphism, then there exists a unique arrow from the quotient into H, which makes this diagram commutative. Okay. So now, okay, you can show that this exists, but then it remains to prove the good properties of the quotient. And so the proof here, the existence proof of the quotient, it uses a certain finiteness theorem about these different algebraic groups. And the finiteness theorem says that every sigma Hopf ideal in a finitely sigma generated sigma Hopf algebra is itself finitely sigma generated. So it's finitely generated as a difference ideal. That's kind of you can think of this theorem as a strengthening of the classical basis theorem. So it's kind of surprising actually that this is true, because the basis theorem, the Ritz-Rautenbusch basis theorem, it usually just says that the perfect difference ideals are finitely generated as perfect difference ideals. Not even perfect difference ideals are finitely generated as difference ideals. So, but if you have this group structure, then you're always in this finite generated situation.
But this is true in the differential case as well, for example.
Yes, but in a differential case, it's much easier to prove right. And so maybe you can think of this, you can formulate this theorem more intuitively by saying that if a different algebraic group is a group defined by algebraic difference equation, then this theorem says that any different algebraic group can already be defined by finitely many different algebraic equations. So if you try to naively translate the Jordan-Hölder theorem to different algebraic groups, you see quite fast that it does not work that directly. So if you look at GA as a different algebraic group, you can see that it does not have a decomposition series. So one can show that in characteristic 0, every different algebraic subgroup of GA is defined by a linear difference equation. And so if you have a proper different algebraic subgroup, you can always find one which is properly contained between the two. So you can just take any non-trivial linear difference operator L prime to construct a proper intermediate group here. And so, what can you do? But it's kind of, I think, GA, it's hopeless. Do you have a question?
So this somehow relies on the fact that you don't force your sigma to be injective, right?
Which statement?
That this building this intermediate H prime, because if you were working over different fields rather than different strings, then
I think here it's not really I mean, I think that's even true if you you only consider perfect ideas. I mean, you can always take any L prime basically. Yeah. So you think? I mean, there's probably no point in trying to. I mean, the point of the Jordan-Hölder theorem is to decompose possibly quite complicated groups into simpler pieces, right? And so GA, okay, maybe GA is already simple enough. So I mean, there's probably no point in trying to decompose GA, right? Okay, so essentially we say, okay, GA is simple, and but what should be then the general definition of a simple or almost simple group? So now we observe that here the coordinate ring of GA is the difference polynomial ring in one variable. So as a ring, it does have infinite full dimension, and but the coordinate rings of the subgroups, they all have finite full dimensions. So in terms of the difference dimension, so the difference dimension of G here is 1, and the difference dimension of the proper subgroups is always 0. So you can say, okay, so compared to G, the dimension of the subgroups is really small. So the subgroups are really small compared to the full group, and we take that as the definition of almost simple. So we say that a difference algebraic group G of positive difference dimension is almost simple if every normal proper difference algebraic subgroup has sigma dimension 0. Okay, so this is pretty close to having no proper normal difference algebraic subgroup. Okay, so those small ones you don't.
It's not enough to have just lower.
No, so that's the definition of almost simple. So to have nothing which is lower, that would be called strongly connected. I'll come to that on the next slide. Okay. So, but here we're using this notion of difference dimension, and maybe I should explain that a little bit more what that actually is. And so it's not completely clear, but it's not totally obvious how to define the difference dimension of an arbitrary finitely difference generated K sigma algebra. To finitely difference generated, you can also write it like that. So there exists a finite set in R such that R is generated by the iterates of sigma of B, and then you can show that this limit here, it exists and it does not depend on B, and then you call it the difference dimension. Here it is, here you have I plus 1 things, and it's kind of the average thing here. And one thing which is quite funny about this definition is that it's not always an integer. So you can show that. It's quite easy to compute the difference dimension of this thing. It's 1/2, and it's kind of maybe it's a bit strange, but it's also kind of reasonable, I think. So because this equation defines a different subvariety of A1, and it shouldn't have difference dimension 1, so because it's really properly contained in there. But on the other hand, it shouldn't have difference dimension 0 because as a ring it has infinite full dimension. So that difference dimension 0 is kind of finite. Okay, so it kind of makes sense that it's right in between. And so I'd be really interested in knowing which kind of numbers actually can occur as this dimension. So all the examples I know they are rational, but probably there could even be an irrational number as a dimension. And I don't know which rational numbers occur as dimension.
Why do you use an average and not use a dimension polynomial?
Yeah, so it does not exist, the dimension polynomial. So so really, so if R is an integral domain, and maybe this sigma injective, okay, then you have the dimension polynomial, and maybe still if the zero ideal is perfect, then you're in a classical situation. But really, so here the problem is with you might have a lot of zero devices in R, and then so it's kind of the dimension polynomial does not exist, but that's like the leading coefficient of the dimension polynomial in some sense. Right?
So if the ideal is prime, it coincides with...
Yes, precisely, yes. So if the ideal is prime, then this dimension for large I is it's really, so it is d times I plus 1 plus e. So this dimension there is this for large I. So if you divide by I plus 1, you really get the d in the limit, and that's the dimension.
Well, the natural thing to do in other contexts when the idea was not prime is to decompose it and then take the.
Yeah, but so potentially there is not a single prime difference ideal in R. No point in composing anything. Okay.
It's not good.
Yeah, but anyway, so here in our situation, one can show that for the Hopf algebras, which we are really interested in, it's always an any integer. So it's, okay. Yes, and so for Hopf algebras, you also have this dimension polynomial. Okay, and also so the notion of dimension is about behavior. For example, for quotients, you get this expected formula, which you have for algebraic groups too. And you can also prove that.
So the ideal generator YY is not prime?
This
in the previous example.
This ideal is not prime.
By Y, if you add Y.
If you add Y, yeah, I mean then it's I mean the ideal generated by Y is prime, yeah, sure. Yeah, it's just the point.
The components.
Yeah, I mean yes, so if you take the perfect closures, it's just a point. Yeah, like geometrically, I mean in the naive sense, this is just a point. But somehow it's a really fat point. I mean, it's extremely fat. I mean, okay, it's kind of so the point is Zariski dense. It's only a point, but it's Zariski dense in a fine space. So it's kind of really big. Okay. So you can prove a dimension theorem for different algebraic groups. And so if you have two different algebraic subgroups of a different algebraic group, then the difference dimension of the intersection is bounded by these natural formulas. And this is another instance where different algebraic groups are much better behaved than arbitrary difference varieties. So that's not true for arbitrary difference varieties, but it's true for different algebraic groups. Okay, now we come to the strong identity component, and so you had a different algebraic group of positive dimension, and one can show that among all different algebraic subgroups which have the same difference dimension, there exists a unique smallest one, and it's denoted like that, and it's called a strong identity component. And so the proof of this statement, it uses this dimension theorem we had before, and it also uses this finiteness theorem from a few slides before. And then you say that, okay, this group is strongly connected if it's equal to its strong identity component. So that really means, okay, it has no proper normal subgroups of the same dimension. And for example, a smooth connected algebraic group, if you think of it as a different algebraic group, then it is strongly connected. But there's something which maybe a bit counterintuitive. So the strong identity component, you can think of it, you should think of it in fact as an analog of the usual identity component for algebraic groups. And it need not be normal in G. And that's kind of counterintuitive because you think it's a characteristic subgroup, so it's stable under any automorphism, because it's like the unique smallest one with a certain property which is preserved under any automorphism. But that's not good enough to get you something normal. So let's look at the example. And so, but that's a point where it's really crucial that sigma is not injected. Okay, so here we have, you look at this difference algebraic subgroup N of the additive group, and as H we take the multiplicative group, and you have an action of H on N by scaling, and so we can form the semi-direct product. which is then given by this multiplication. And so it's easy to see that the difference dimension of G is 1, but we also have this difference algebraic subgroup H, which has a difference dimension 1. And so, as we already noted before, so Gn is strongly connected. So the strong identity component of G is H, and H is not normal in G. So N is normal in G, but H is not normal in G. Okay. Well, so that's kind of a problem, and it's not so easy to get around this. But the following proposition does fix this problem in some case, and so it says that okay. So here we need this assumption on a base field, which I'm not really happy about, but I don't know how to do it without it. So you assume that K is algebraically closed and inversive, which means inversive means that sigma is an automorphism. And then if G is strongly connected and H normal difference algebraic subgroup of G, then you can show that the strong identity component with H is normal in G. In particular, it's normal in H, but it's even normal in G. So one more definition before we can come to the formulation of the Jordan-Hölder theorem. As isogenies, so a surjective morphism of difference algebraic group is called an isogeny if the difference dimension of the kernel is 0, and two difference algebraic groups are called isogenous if you have this kind of isogenies. And so the idea of isogenies is to consider, so that's all, in fact that's really the idea of the Jordan-Hölder theorem, to consider everything up to difference dimension 0. This is what makes it work. And so one can show that to be isogenous defines an equivalence relation on the set of strongly connected difference algebraic groups. And so with this notation we can now formulate the Jordan-Hölder theorem. Okay, so we need this assumption on the base field, and if G is a strongly connected difference algebraic group, then there exists a subnormal series. It's a property that each GI is strongly connected and the quotients are almost 0. And if you have another such series, then these two series have the same length, and up to a permutation of the quotient groups, these groups are isogenous. Okay, so you cannot get isomorphism, but okay, they are isogenous. So they are the same up to something 0 dimension. And, yeah, I think I'll skip that.
Excuse me.
Yeah.
In the definition of isogeny, you have a G and an H1 and an H2, right?
Yes.
So now you're giving the two quotients. So what is G?
So you say that there exists a G. So you say H1 and H2 are isogenous. If there exists a G together with isogenies.
There exists a G. Oh,
yeah.
Right.
Yeah, so the uniqueness actually is easier, to prove in this case. So you can prove the Schreier refinement theorem, and this then it implies the uniqueness statement in the Jordan-Hölder theorem. And so once you've proved all these isomorphism theorems, then it's really more or less you just copy the standard proof for finite groups. And but so that the existence is a bit more challenging here because of this problem that we don't have normality. But I guess okay, that's all I wanted to say today. And so if you're interested in the details, you can find them on the recent paper on the article.
Questions?
So for the almost simple groups which appear in the decomposition, is it your guess that if they happen to be non-commutative, then they're actually perfect or not?
Yeah, so actually one can show that if your base field is algebraically closed and inversive, then strongly connected implies perfect.
Oh, it does.
Even integral, sigma integral. So if your base field is algebraically closed and inversive, then strongly connected implies that the coordinate ring is an integral domain with sigma injected. Yeah, and that's essentially
No,
because
I mean,
That's a question.
I mean something.
a perfect in a not in the sense that the ideal being perfect, but like this cool property. Okay, sorry. Okay, I was thinking about something
Yeah, no, I know what you're
different.
thinking.
Okay, I don't know. I have no idea. No, about that.
I guess that's your future theory. Other questions? I have a question about the first example, the Bessel functions.
Okay.
Could you highlight again? So how do you see that relation from?
Yeah. So to see this relation, you should write it in a matrix equation. So if you write there's another. There's a similar relation for the second Bessel function, and if you write the fundamental matrix, so if y is then, if you take j alpha, y alpha, the second, and y alpha prime, then you can write it like this, where b is rational functions in x and alpha, and this is so at this equation really corresponds to this equation. So maybe if it's even more intuitive, you can probably write like this lies in the base field, that this equation is really kind of this equation. It kind of corresponds.
So one can, you claim one can read off it immediately from the equation defined or not? You have to do something else.
So what we actually do to compute it, okay, yes. I mean, these equations are well known, so we compute the Galois group from this equation, right? So, but I mean, if you, yeah, I mean, but if you know, if you say, okay, but if you assume you know the Galois group, yeah, I guess you can then, yes, if you know the Galois group, you can compute this equation. But of course, I mean, the question is how to know the Galois group.
This is my question. Yeah, not clear. It's not clear.
How to compute?
Yes.
How to compute the Galois group?
No. How to find the equation from the Galois group?
Middle equation.
Yeah. Yeah, I think I guess it's more or less considered to be equivalent, right? I mean, to compute all the equations and to compute the Galois group, more or less.
Well, suppose you're given the last line. How to find the middle one? That's the goal, right? So that's our goal. So we'll compute the last line, and then we'll say that we know how to find the middle one.
You're asking the inverse problem?
No, it's not an inverse problem. It's from knowing the Galois group, find the relations. Find the Picard-Wilson. It's not an inverse problem. The inverse problem is given a group, find out if it can occur as a Galois group. But this is given the equation to find the group, find the Picard-Wilson. Not knowing that possibly. There is not a good algorithm yet.
No, okay.
For the future.
Okay.
That's for the future.
No, there's no good algorithm to do that.
Right. Other questions?
They didn't finish reading the last slide.
Okay.
Too bad.
That one?
No, the very last one. Yeah, that's
I was really fast on that. I know that.
Thanks.
More requests?